Where do we start? So the motivation behind this work was the realization that as programming language researchers, our ability to experiment with our ideas rests very much on our ability to implement them and get to try them out. Because having an implementation helps us explore the design space and understand what works and what doesn't work, and therefore refine our ideas and come up with new ones as well. So tools that can help in terms of cutting down on implementation time and therefore unlocking further experimentation are meta-languages. And I think the breadth of research using tools like PLT Redux and Racket and the K framework and OTT and so on demonstrates this fact. So the takeaway of this work and this talk is that lambda Prolog, higher order logic programming, is quite a good tool. It's quite a good meta language when it comes to quickly implementing advanced type systems, where some other tools maybe it's not their strong point. And the reasons for that are multiple. I would highlight the fact that the rules that we write down once you know the language are quite concise and quite readable in themselves. They're very expressive, like they can handle real complexity of real research ideas. And they're incremental, meaning that we can work on features independently, and when we work on something new, we don't have to go back and change things to existing features, which is kind of nice for this kind of experimentation and refinement process when we're exploring an idea. So yeah, I've worked on a new implementation for lambda Prolog, which is called Macam, which tries to tailor itself to doing prototyping for type systems, more or less. And I have to say that it's more expressive than that. It doesn't have to do just with type systems. It could be used for compilation between languages and transformations and so on. But yeah, in the paper, the main thing that we do is we show a big example where we implement quite an advanced type system. And the code for all of this is within the paper. And also, not just that, but we also have a lot of standard library definitions and so on that these rest upon. There's other things in the paper as well. We had to develop some things that are relatively novel. So for example, how we do structural recursion nicely in lambda Prolog so that we only write the important cases for a structurally recursive judgment, and the boilerplate is just automatic in a sense. And we had to make some folklore things a bit more clear, like how to do complex binding structures when lambda Prolog only supports single variable binding natively. Another thing we found is we can do GADTs in lambda Prolog with no additions. And also we show how to use reflective predicates to reuse parts of the type language, parts of lambda Prolog other than just binding. The other thing that's in the paper is it's written in what has been called an unconventional style, and there's these people in it. It's a dialogue between Rosa Eskenazi and Hagop Tomboulian. So these are Smyrna Trio. These were the pioneers of the Rembetico music form in Greece, which is based on Makam, which Makam is the mode of improvisation in Arabic music. So yeah, Rosa Eskenazi, she's reimagined as a PhD advisor, and Hagop Tomboulian as her student, and Lambros is a minor character from next door. So there's more things in the paper along those lines. I'll leave that as a surprise. So let's continue. The main thing that I'm going to show in the talk is a little bit of an example of how to use Makam. And I won't be able to give the full details, but just to give you a taste of things. So let's do the simply typed lambda calculus, which is kind of the hello world example for lambda Prolog. So this is it. You know the rules above. The rules below, maybe you haven't seen, but let's see how we read them. So in lambda Prolog, the consequence of a rule comes first, and then the premises come second. So here we're saying that the type of application of E1 to E2 is T prime when the type of E1 is arrow t to t prime, and the type of E2 is t, which is quite standard. And for lambda abstractions, the way that we read the consequence is this. We say that assuming a fresh variable x, which is a term, and assuming that the type of x is t, then check that the type of the body, which is the binding applied to the fresh variable that we have, so that we get to the body, is t prime. And these x and this type of, they are like local definitions that are only in effect for this rule. So with these two rules, we already have a type checker. So let's see. Okay, we got the type of the identity function. And notice that, of course, here we don't have enough information to figure out what the type of t prime is, but that's left as an uninstantiated unification variable. Of course, there's a few things that I've omitted so far, and those are the declarations. So Macam is a typed version of lambda Prolog, so we have to specify the types that we use. So first of all, we declare the types or sorts for terms, for object-level terms and object-level types. And type of is a predicate corresponding to the typing judgment, where we relate a term to its type. We also have to define the constructors for application, lambda abstractions, and arrows. So this is how we would write that on paper, typically. And if we make the binding structure of this more evident on paper, like similar to what Bob Harper does, for example, in Practical Foundations for Programming Languages, we would write this as this, where I've also made apparent what the name of each constructor is. So in the lambda case, which is the more complicated one, we show that the type itself doesn't have binding, but for the body we have a single variable binding of x. And from this form, this is direct transcription to Macam, where for the lambda case we say that it takes a type and it takes a single variable binding of a term into a term, represented as the meta-level function type in the standard higher-order abstract syntax style, and that yields a term. So yeah, that's all there is to the lambda calculus. And now let's move on to something a little bit more complicated, which is multi-arity functions and multiple mutually recursive blocks, LETREC. So in that case, what we would write on paper is something like this, where we have a simultaneous binding of multiple variables standing for the multiple uncarried parameters to a function. So this is slightly different because now we don't have single variable binding, we have multiple variable binding. And the way we transcribe this into Macam is like this. We say that we have, like, lam_many has to bind many terms into a term. And this is a type that we have defined in the language itself, using the support for single variable binding, but it's not something that's built into the language. And you can see the details of that in the paper. And with that, we can also write the typing rules. Again, we have to make use of some things that we have defined in the language, like open many and assume many. And the way to read this is that, create, like assuming as many fresh variables as needed, x is getting to the body e, and then assuming that they have the types t's, then the type of the body is t. And this gets extended quite nicely to other things like, for example, LETREC. So this is how we would write it on paper. Again, if I make the binding structure apparent, what is happening is that x is in scope both for e's, which are the definition, and e, which is the body of the LETREC. So this is one way that I could write that down. And this, again, is easy to transcribe to Macam, where I say that I bind many terms into a tuple of a list of terms and a term. So the list of terms is the definitions, and the term is the body of the LETREC. Now, the thing is here, I have lost the fact that I have to bind as many things as there are definitions. Fortunately, we can use GADTs for that. So we can have a type like this that says that I'm binding n terms into a list of length n representing the definitions and a term representing the body. Now, the cool thing about this is that this form of GADTs was already supported in the original design of lambda Prolog from 1989, like many years before GADTs were even a thing. And yeah, I think we were the first ones to realize it. So you can read more details about in the paper as well. So this is the typing rule for LETREC. I don't want to go through the details, but it's quite similar to the lambda many, and it's very concise. Now, the last thing that we're going to talk about is ML-style generalization. And the way we are going to do this is we are going to reuse the notion of unification variables that exist in the meta language in lambda Prolog. So if you saw earlier when we saw the example of the identity function, the t prime to t prime, the t prime was a unification variable that we couldn't further determine, and we can use that to pull that out and close over it so as to create the closed polymorphic type for the identity function. So yeah, there's two things that are going on here. One is this use of like extra logical things to look into the structure of terms. The other thing is that we're going to use generic code so that we don't write a lot of boilerplate action. And you know, the first choice is something that some people might not like because we have to use extra logical predicates, but we could instead do like a deep embedding of unification variables, and if that's something we want to do. But the generic part, that's useful in all cases, I would say. So this is the typing rule that we'd usually write. So this part is the generalization, and that's the tricky part. Otherwise, this is quite similar to a normal let. And the way that generalization is defined is this. What we have to do is take a look at the type that we have determined, figure out the free variables that are in it, and get rid of any free variables that also show up in the context for this to be type safe. And then once we have that, we can close over that and maybe rename the variables, and that's how that works. In this case, what is free variables here will be the uninstantiated unification variables that we'll have determined with the rest of the typing judgment. Okay, so let's see how this is written in Macam. So it's split into two rules. So what I'm doing here is instead of doing all variables at the same time, I'm doing one variable at a time and recursing. So the first case is the base case where there are no more unification variables to find. So find unif takes a term and sees if there is a unification variable A in it. And of course, this uses the extra logical features that I talked about. In the other case, I am finding a unification variable A. I am recursing, replacing the unification variable with an actual fresh variable so that I don't end up in an infinite loop. And then I proceed to generalize. And then in the end, I get the types of the environment, and I only abstract over it if the unification variable does not show up in the environment. So that's what hash_unif does here. So yeah, this depends, of course, on the definitions of find unif, replace unif, and hash_unif, but that's where we use generic programming to make those very simple to write and cover all cases with code of roughly this kind of size for all of them. So let's see what this does. So replace unif is what changes, a where to a what, depending on if it matches the which. But the main thing is that these two are the important cases where we decide whether we have to replace a unification variable or not. And then all of the rest of the stuff is handled by this generic rule, which uses this structural recursion, which is basically something that we have defined in Macam. and says that in this case, just do a structural recursion over the term that you have, and then in each subnode use the same function for the recursive call. So the nice thing with this is that there is no code here that is specific to the types that we have so far in the language. So we only have to give the important cases. And this still holds even if we add completely new types that weren't there before. So for example, in this case, let's see, do we get the type of the identity function? We do. And here, yeah, this is slightly different from ML, but yeah, I just want to show the polymorphic type that we get. But the main thing is that this still works even if we add new things to the type system that weren't there before. So for example, let's add tuples. So let's add a tuple that takes a list of terms into a term, and let's add the multiple product type as well. And then let's write down the typing rule for this. So tuple of these is product t's if we pairwise do type of on the expressions and the types. Okay, so we have that. And now let's see what happens if we take this code and, for example, here in the body, I'll use a tuple. Okay, so yeah, we get the type that we expect. So it's the for all A to product of A and A. And note that this happened without adding anything that didn't have to do with the types that we already have. So these kinds of generic predicates work even though we might make changes to our type system. So some cases of the expression problem, let's say, are handled quite nicely in lambda Prolog, especially using these kinds of generic predicates. I think that's all I had. So I'm glad to tell you more details, and there's more details in our website as well, and in the repository for Macam. And I'll be happy to take questions. So thank you very much.
All right. Have you considered encoding linear typing or some other sort of substructural discipline and how that would interact with the way lambda Prolog supports your variable environments?
So yeah, we have considered it. There is, so in some cases, if we do a deep embedding, things work out. Like we have to encode like the linearity part of judgments, and that works out nicely. In terms of something that is, that feels a little bit more native, I think, more additions would be needed, kind of like what linear left does or something like that.
So you've talked a lot about typing. Could you also express reduction in this system? And then could you even go so far as to proving progress or searching for counterexamples to progress?
So definitely, like reduction we can encode. Actually, in the paper, I didn't talk about it, but we have like a reduction predicate for the language that we show. In terms of doing proofs, not within the language directly. So it's let's say the simply typed fragment of a left. But you could use tools like Abella, for example, that allow you to reason about definitions written in lambda Prolog to do proofs. Another thing is that in general, one thing that we're thinking about Macam is using it to do translations between existing languages. So we could use Macam to translate our definitions into, let's say, code and then do our proofs there.
Okay. So the rules that you've shown were all syntax directed. If I wanted to add like a subsumption rule or something like that, can I do that naturally, or do I have to translate that into the syntax directed version first?
In some cases you can, and in some cases you can't. So it really depends. But yeah, I would say that, so for, let's say, in some cases we can make small changes to how the rules work, so that subsumption is localized to specific rules that only deal with subsumption. And we do give an example of that with the conversion rule in the paper. In other cases where, like a deeper change is needed, in that case, you'd have to switch to like an algorithmic formulation or something like that.
Is there some way that you can take advantage, you can use the higher order abstract syntax to create invalid terms? What support is lambda Prolog giving you for limiting the structure of terms?
So lambda Prolog in itself, it does not have any exotic terms as higher order abstract syntax would have in Haskell, for example. The reason for that is that the function space is very constrained. So we can't do things like pattern match on an argument and stuff like that. So the normal functions in lambda Prolog map exactly to single variable binding. That said, we do have computation, which is segregated into the prop sort. But that's the only way to do computation, basically.
All right. Well, let's thank Antonius again.
Thank you very much.